Okay, in the last video we discussed why fluorescence is so sensitive. Now we're going to get into fluorescence experiments themselves. One aspect I want to discuss before we get too deep into things is that there are two lights to keep track of in these experiments, right? There's the light that we're sending in, some of which is coming out the other side, and then there's the fluorescence emission that we're actually trying to detect. So how do we keep track of the different light photons? How do we make sure that we're detecting this fluorescent light and not this transmitted light from the original source that we're sending into the sample? So there's two ways that fluorescence gives a distinct signal from the light that we're shining in. Two ways that fluorescence or fluor gives distinct signal from light shined in. Light shined in. And for the record, we would refer to that shined in light as the wavelength of excitation. The wavelength that is absorbed and excites the molecule, which will eventually lead to fluorescent light emission. The first way has already been addressed previously. The wavelength of that emitted light is greater than the wavelength of the excitation light. And we already covered the reason for that in the last lecture and in today's recap. So that alone is a rather big tell, is that the emitted light is different in wavelength than what we're sending in. The other thing we do that has not been discussed is we set the detector perpendicular to the path of light shined in. So let's write that and then see what I mean. Detector is perpendicular. Detector is perpendicular to path of light shined in. So here's what I mean by that. Imagine that we have a sample in a cuvette and we have a light source that's shining in light. And let's say that some of that light is absorbed and some of it makes it out the other side. And then let's say that this sample is fluorescent, and when it re-emits light, the wavelength that primarily comes out is red. Well, the emitted light is completely random in terms of what direction it's going to come out in. Some of it might actually even go backwards towards the original light source, and some of it will go forwards along with that transmitted purple light. There is really no favored source of direction when it comes to these molecules emitting light. It's random and it's equally probable in all directions. So we put a detector 90 degrees apart from that light source. Because the light source is not random. It's absolutely pointed in a specific direction and shines light through in this direction. And almost all of the transmitted light will keep on going through that path. A very small fraction might be scattered in different directions, including towards that detector, but by placing the detector perpendicular, we minimize the chances of any of this initial purple light making its way down here. So any light that we do detect is almost certainly fluorescent light. Now some of you might be thinking, well wait, if we're only going to detect the light that comes out in this direction, we're missing all of this other emitted light. Isn't that a problem for our analysis? And the answer is no. Because let's say that this particular sample shined that many red fluorescent photons out. Then we measured another sample that was twice as concentrated. Well, that will shine out twice as many red photons in every single direction, including towards the detector itself. And so it really doesn't matter that we're missing all of these other photons. What matters is that, as far as the detector is concerned, we're still counting twice as many photons as before when we double the concentration of our sample. So we can still absolutely relate the emission intensity of light to the concentration of our analyte. So between the detector being perpendicular and our light wavelengths being different, we can absolutely distinguish fluorescent light effectively from the light that we're shining in, or what we would call the excitation light. And so with that in mind, let's get into the actual experimental setup. So here we go. I'll start by saying that a fluorescence experiment happens in two major parts. And the first part doesn't even involve tracking fluorescent light. It's all about figuring out what light should we send in the first place to excite the sample. Because if we can't excite the sample, then it can't relax, in which case there is no emission. And so the first thing we do is very similar to a UV-Vis experiment. We just send in a range of wavelengths into the sample itself. And then again, we have a detector perpendicular to the excitation source, and we measure how much emitted light comes out the sample. And so if the light that we're sending in isn't absorbed in the first place, then we don't expect to see much emission intensity either as a result. But eventually we will find wavelengths that when sent in are absorbed and produce a significant emission that we can detect. And once we find the wavelength that is exciting the molecule the most, and thus in turn yielding the most fluorescent light coming back out, then we know let's only send that wavelength in and then track the fluorescent light that comes out as a result, because we want the highest signals possible. But before we get into the fluorescence part, let's just delve a little bit more into this excitation part here that I've been describing. Alright, to control this thing, I'm going to use a bit fancier of a controller, and I'm going to do it in the style of a Let's Play video to make it a little bit more interesting. The footage will definitely be a lot more boring than a video game, but hopefully the commentary will be less inane than those Let's Play YouTubers. So let's start by shining in some purple light. Exciting. And we can see that according to our spectrum, there's no light being emitted as a consequence, and that's also depicted in our picture up here. So let's just keep shining in some wavelengths. Let's go to blue light. And still nothing. Let's go to green light. And still nothing. Let's go to yellow light. Alright, now we can see some emission intensity. So clearly this particular wavelength is being absorbed and causing some fluorescent light to come out of our sample. Let's see that in the top right picture. Ah! That was intense. Okay, let's keep on going though. This is being absorbed, but maybe we can do better. Orange. And this produces an even greater emission intensity. So clearly this particular wavelength is absorbed more frequently than the previous one, and thus causing greater fluorescence. Now let's go to red light, and we see that this light is not being absorbed well and produces pretty much no emission. And so clearly the best light to send in to get a strong fluorescent signal is the orange light. So now we're going to program the instrument to only send that light in. Such a nerd. And then we're going to track that emission. So we're going to watch all of the different wavelengths of fluorescent light come out of the sample and find which one is emitted the most. So again, we are shining in only that particular excitation light that causes the max excitation. We will measure all of the emission intensities of wavelengths coming back out, and we will use the highest signal for analysis. And so we shine that particular orange wavelength in, and then let's say we observe this fluorescent spectrum coming back out. Notice it's a mirror image to the excitation spectrum. We already covered earlier that we should expect to see this in this class. And then of all of these wavelengths that are coming back out of the sample or not coming back out of the sample, the only one we care about is the one that produces the highest emission intensity. And this number alone is what's going to go on something like a calibration curve if we're doing a quantitative analysis. We collect all of this data just to get that one intensity reading so that we in turn can make the most reliable calibration curve possible, knowing that we're using the maximum signal available. Now you should quickly pause the video and ask yourself, what would the emission spectrum look like if instead of shining this wavelength in, we shined this wavelength in? And the answer is we would get the exact same shape, it would just be lower in intensity all around. Because this light is absorbed, which means it will produce emission, and the emission wavelengths should be the same no matter what light we're shining in, because it's all based on those energy levels that we discussed before, which aren't influenced by what light we're actually shining into the sample. But because this particular wavelength isn't absorbed as much in the first place, it doesn't produce as much subsequent fluorescent emission. But if we were to send in, say, this wavelength, well, that's not exciting the molecule at all, which means there's no emission at all. And so our fluorescence spectrum would just be a flat line. And so this is the basic theory behind what we do in a fluorescence experiment. Now let's get more into how it looks in practice.
So here is our fluorometer, and here is a fluorometer cuvette full of a fluorescent chemical solution. One thing to notice is that this type of cuvette is clear on all sides, and that's important because remember how this works. Light is going to be shined into one side, and in principle it comes out the other, but we're not really interested in measuring the light that makes it out the other side. That's what we would do in an absorption experiment. In this type of experiment, we're interested in the light that's subsequently emitted upon light being absorbed. And emission happens in all directions, at all angles. And we're particularly interested in capturing the light that's emitted at a 90-degree angle, perpendicular, from the light that's going in, because that has the lowest chance of interference between the two different lights. And so now I'm going to put the cuvette into the fluorometer itself. We can see over here there's this opening, and that is where the light source is. It's not really easy to show you the lamps in this instrument, so I'm not going to bother. But light will come in from there, hit the sample, and then the light that we're interested in detecting will be emitted at this perpendicular angle, and our detector is in there. So now I'm going to start taking some data. And the first thing I'm going to do is figure out what wavelength of light excites the sample the most, just like what was described earlier. And so what I've programmed the instrument to do is send in light of 280 nanometers to 520 nanometers and scan for emitted light of this longer 530 nanometer wavelength. The more a wavelength of light that I'm sending in is absorbed in the first place, then the more of that longer wavelength light should be emitted as a consequence. So here we go. And so there's our data, and the wavelength that excites the sample the most is 448.03 nanometer light. And so now I'm going to take some fluorescence emission data. And so all I've changed in the settings is I'm now in emission mode, so I'm scanning for emitted light. I've adjusted our wavelength range to be longer than before, which makes sense based on the theory we've learned. So my range is from 500 to 620 nanometers, and I am shining in light of 448.03 nanometers. In other words, the wavelength that we found excites the sample the most. And so let's start taking some data. And so this is what that looks like zoomed in. And so there's one major fluorescence peak, and the highest intensity signal is actually at 527.01 nanometers. Now, what would this spectrum have looked like if instead of sending in the wavelength that was absorbed maximally, I had sent in the wavelength that corresponds to that second lower intensity peak? In other words, let's send in 374.00 nanometer light and see what happens. The new spectrum has the same shape. The peak intensity seems to shift it a little bit, but that's probably just error in the instrument. You can see the peak does have some noise in it. But the general shape is the same, which is to be expected, but the overall emission intensity across the board is lower, which also makes sense. Since we sent in light that wasn't absorbed as much in the first place, well, there won't be as much subsequent emission. Now let's try sending in some light that's just not absorbed much at all. So 320 nanometer light. So I'm going to send in, and let's start it. Much lower intensity, which makes sense because not much of that 320 nanometer light we're sending in right now was absorbed in the first place, so there shouldn't be much fluorescence. Now, you may be noticing that the emission spectra are not perfect mirror images of the excitation spectra, and sometimes that does happen for reasons beyond the scope of this class. In this course, we will still by default assume that mirror image spectra will occur in any example problems you do.
So that's the logic of how we acquire the data. The final concept to discuss is what we do with that data, but it turns out there's not much new to learn compared to what you've already learned from the absorbance experiments. Once we cover that, we'll link everything together with this experimental example, but we'll do all that in a future video.